Continue from previous video. In previous video I found one typo here that can be corrected here. That was VU as mean. That is typo. That's corrected here. Now continue from previous video. We stop here. Now we need to calculate VU as minimum. This equation is given in the clause 16.4.4.3 on page number 290 in 3600. So that is written here clearly, and that's copied. That's copied here. Now in this case VUF equal to 0 because we don't have any steel fibers, and VUS minimum equal to 0.1 BV D0 square root FC. Now 0.1 BV is 350. I think given in the questions the width of the beam is a 350 millimeters. That is given here. D0, we calculated D0 value as a 586 millimeters. So that is D0 times by square root 32. The characteristic strength of the concrete is given 32 megapascals. Now that's simplifications. The calculations give 116022.1 Newton. Now if you divide by thousands, it's given 116 kilonewton. Now VU mean, that we written here. VU mean, that is the summation of concrete and the steel. Concrete has a 157. The capacity of the concrete we calculated 157. That substitute here 116 we just calculated. So VU mean is 273 kilonewtons, and if you multiply by the capacity reduction factor 0.7, it gives us 191. Now the minimum fitments will be provided everywhere where you can just correct this one, where V star is 191 kilonewton. So we're going to look at the shear force diagram, and we're going to draw the line where you have 191 kilonewton shear force. That is the minimum shear force that we have it. So in the shear force diagram, if I draw the line here, which is here, let's say this is 191 kilonewton and this one is, let's say, 191 kilonewton, we can find what distance that we are going to provide minimum reinforcement. So this is the zone that has a minimum reinforcement that is covered by 191 kilonewton. Now to calculate those distance, we can use the straight line equations. First of all, let me find this distance where the shear force is 0. So shear force straight line is a slope 150. That slope is nothing but that given in the questions, 150 kilonewton meters, and it's going down, so it's a negative slope. So it's minus 150x plus the intercept is 343. Shear force is 0, so we need to find this distance, let's say x. So if you simplify that one, x will give us 2287 millimeters. Now similarly we need to find this distance. What is this distance from support A where it hits the 191 kilonewton? That is our V minimum, the shear force. So in that case we can take this straight line equation, minus 150x plus 343. We substitute 191 because that's the shear force where we want to calculate. X we need to calculate. This x is given 1013 millimeters. Similarly we can work out the other side of the close to the support B where we have 191 kilonewton, that is kilonewton. We can get the line again, V star minus 150, the slope is minus 150x and the intercept is 437. We substitute 191, that's give us 1640 millimeters. So we found this distance, and we know this distance is 5200. We know that this distance is 5200 millimeters because that is given in the questions, saying that from support A to support B is 5.2 meters. So we can provide the minimum spacing here in this zone. Now what is the spacing here? That we can use this equation. S maximum is the area of let's say this is ASV times the yield strength of the fitment over maximum of 0.06 FC dash on 0.35 BV. Now ASV we calculated in the last video, that ASV has a 160 millimeter square. So we substitute 160 yield strength of the fitment. So we can assume here as well FSY dot F is 250 megapascals. That's the yield strength of the fitment. So yield strength of the fitment we substitute 250, and maximum of 0.06. Concrete strength is given in the questions, 32 megapascals. and 0.35 BV also given in the question. So width of the beam 350 millimeters. Maximum of this simplification gives 0.34, 0.35. So that is the maximum is 0.35 multiplied by 350. That is your BV. So maximum spacing is 326 millimeters. So in this zone we can provide the spacing of 326 millimeters. So if I draw this beam here with the supports here, if you remember the question, so in this zone that in the middle where the shear force is minimum, which is 191 kilonewton, and that we predicted. So we can provide this 326 millimeter. We will rationalize this one because this is not critical zone. We this is the maximum, this one, but these are the critical one that we need to find. So we will rationalize this spacing based on these other two predictions. Now let's move on. Now this is first one, we done it. Now let's talk about the reinforcement, how much fitments we're going to provide close to the support A. When we have a support, say where you have a higher, we found how much spacings we're going to provide in the middle, right, 326 millimeters. But now we are working in this very critical zone that has, because it has a high shear force. So we need to work out how much spacing of the fitments we're going to provide in this zone. So at support A, cracking cannot extend into the support. So please note, when you have a supports here, we don't have cracking starting here in the support zone. When you have here, the cracking generally start when it's past this, because of this concentric force effect, the reaction force effect. You don't have a cracking here. The cracking generally, the shear cracking generally start just some distance from the supports. So to calculate the design shear force at distance d0 from the face of the support A, so we can say that, okay, this is the zone where the cracking going to start. So we are interested in finding the shear force at this point. Now this Australian standard has given these notes as well. If you look at the page 115, at the end of the page, it has a clause 8.3.2.3.2. It has says that a distance d0 from the face of the supports. You can read about it. So it's an important line here, that if you like to see maximum transverse shear near the supports, we need to have this distance d0 from the supports that is given in the standards. So therefore we put the d0, and the support is 300 millimeters, that is given in the questions. Support is 300 millimeters. This is a shear force diagram, and we just need to find the shear force VA star at the distance d0. Now this distance x is nothing but d0 plus 150, because we are taking the shear force diagram from the middle. So this x is nothing but 0.3 divided by 2, which is in the meter. 300 divided by 1000, 0.3 divided by 2, plus this d0 distance is 0.586. We calculated d0 value in the previous video. In the last steps, d0 is 0.586 meters. So this is 0.586 meters plus 340. So this line is nothing but this line is y equal to mx plus c. M is a slope, because we have this loading 150 and is going downwards, so it's a negative 150 times this distance x is nothing but 150 plus d0 plus 343 is intercept, give us 233 kilonewtons. Now that's V stars give us so that is 233 kilonewtons. That is your V stars. Now we stop here, and we're going to continue in the next video. Thank you.